Yes, now you are recorded. Welcome. Present.
I'm going to talk about a project that started for the course when I was in my master's, and now I'm expanding it. So you can tell by the title, we formulate formal proofs in natural deduction in the first order logic, and then export it to LaTeX. So for this purpose, I built a proof system called Durde. It's based on the first order logic with natural deduction rules. It was developed in the Haskell, functional programming language Haskell, and you interacted with this proof system through the interactive environment HCI. And you kind of by little build a proof, and you see the at each step. And then when you build a proof, you can export it to the LaTeX tree. The whole project is available online at the GitHub. This is the example we are going to go through for this talk. So for all x, if ax and bx, then it implies that for all x, it's called it ax, and for all x, bx. To start, I'm going to introduce natural deduction. So probably I think all of you heard about it, just in a couple of short steps. So we have, this is the system for reasoning about logic. So we have inference that are of this form. So we have a list of hypotheses, then we have the conclusion. Hypothesis and the conclusion are the form gamma, then this with dash and then e, meaning that gamma is context. In our case will be the list of formulas, first order formulas, and then from which the formula A can be derived. There are two types of inference rules, introduction rules and elimination rules. That's kind of how we classify these inference rules. Okay, and the proof is then a sequence of steps or inference rules. So basically the proof has its branching structure, and that's why we can call it proof tree. And this is one example. So at the leaves, we have empty nodes, or that's from the assumption, followed by assumption that we can, from the context, prove our formula. So if the context consists of P implies Q, and Q implies R, we can, from assumption, do that P holds, and that P implies Q holds, and then here Q implies R holds. Then we can, using multiple inference rule, derive that Q holds, and then again, exponents derived that R holds. So this is the one way to visualize these proofs and to write them, but there is another one where we can just put assumptions at the leaves. So all of the lists will make current context. as I said, there are introduction and elimination rules. Introduction usually always actually finishes that current connective is visible in the formula, and elimination learns if we have in the hypothesis some connective, then we by this rule and eliminate it. So I'm not going to go through all of this. Probably you're all familiar with it. I'm just gonna say that let's, for example, have this equivalence and the rules for equivalence. There are two eliminations rule. So if A is equivalent to B, then we can derive that A implies B, and we also can derive that B implies A. This will be this is something that we can write like this, but it's not how it's actually implemented in the theater. You will see later details. Okay, and then we have the rules for negation, conjunction, disjunction. Also here we have also two rules. In the theater, it is implemented in one rule. For example, we have these two introduction rules for disjunction, and we actually implement both of these rules in the proof assistant theater. And then we got rules for the logical constant, universal quantifier, and the existential quantifier. So this will be that example that I showed earlier for the relation of this form here. One thing to note here is that I use these two rules. This is actually not, again, this is not how it is implemented in the theater, and we will see the difference. So what's the motivation of this project? Most of the proof assistants actually assist us in writing the proofs, but many of them fail when we try to read those formal proofs. There is like a lot of space like for the works to be done in that area. We'll go through a couple of examples. So if we want to prove this in Isabel, this is as close as we get. We first apply implication and introduction, which will correspond to this step here. Then we can apply conjunct introduction, and this will correspond to this step here, splitting the proofs into two branches, and so on. We can continue proving the rest. So what it will give us? It gives us a list of rules, but it lacks structure. Isabel tried to mask by making this indentation, and when we indent, we actually make a new branch. So another example that we'll see is EuroProofs in Isabel. They actually gives us structure, but we lack. We see that there is a lot of boilerplate code. We see that, for example, we just copy some of pieces of the code, then it's just tedious to write. And then if we use any information, then we cannot get any information actually how to make proof tree from this. Let's see lean. Lean has some structure, but what lean does is not suited for the natural deduction. So this is like the lean uses more general approach, encoding first order logic to types and dependent types. So there is like, if we, for example, want this to give to a student in educational purposes, this will be this will require them to learn about the type theory and everything. And for the entry level in logics, this will be kind of hard. I'm not saying they shouldn't learn about type theory. Of course they should, but just at the entry level, it will be much more easier just with the natural deduction. And then another way in Lean4, what we can do is we can use lambda abstractions to prove the theorem. In Agda, here we can use pattern matching to prove this, but come from fact that again we use lambda abstractions here, and then we for our argument we can pattern match it to their left-hand side and right-hand side. So again, this is where student would probably have to learn about type theories to be able to do this. Okay, so proof system failure is goal oriented, meaning that we have a goal which applying rules changes, and when we get the empty goal, we know that we finished the proof. And theater is split in the two modules. For the first order logic and the other for stating, formalizing, and exporting proof, LaTeX proof trees. Okay, a couple of things in logic. It's implemented in the other. We have a term, can be variable, constant, or the functional symbol applied to a list of terms. We can encode it in Haskell, just saying that var is some string and the function is some string, and then a list of terms. For the constant, we can just say that constants are functional symbol that have 0 arguments. Formula, it consists of logical constant variable, relational symbols, negation of formula, conjunction, disjunction, and so on. We also encode it in Theodore. We have again, relation for the zero terms to be a variable, just a logical variable. So this is an example of that formula from the beginning. To make this formula, we first use implication constructor, then we construct left side, and then construct the right side. Left will be just the universal quantifier here for the variable x, and then conjunctions of ax and bx. Similarly, we can do it for the other side. So now we go to the Theodore module. In order for natural deductions work, we need to introduce meta variables, which will be just a list of strings. We also define assumption or premise for the first order formula. Assumption will be just formula or combined with its name, and then a context or hypothesis is the list of assumptions in the Theodore. We call it assumptions. Then we can define the conjecture or subgoal, which will have three elements: meta variables, context, and conclusion. Where conclusion is just first order formula, and we make constructor for that. And the goal would be natural to define like a list of subgoals. So we can also define a new function that makes given assumptions and the formula that it produces a new goal with empty list of meta variables. One note here, usually we are going to search for assumptions for some particular assumption in the list. So we could also implement this using sets, but usually for our purposes, this list will be small, so we don't have to. We are not going to get so much optimization there.
Don't you get the optimization by needing to?
Yeah, actually,
Or does.
yeah, it actually does. Yeah. So now we can make our goal. We're going to just use this function with empty list of assumptions and conclusion f. And Theodore outputs this. Then we have one goal that gets this subgoal. And now to the proof, we actually just list all of the rules from natural deduction. If you remember, know that I did say that, for example, conjunction elimination will only have one rule. Let me go here. So we have these two rules for the conjunction elimination, and what it does, it actually doesn't change that right hand side of the v dash. It accesses one of the assumptions and then it splits into two. For example, if we have A and B in the context, then it's splits that A and B into A and then comma B. And what we have here also is something that we don't have in the rules. This to do. It will actually represent call in the proof. This meaning that if we are checking the proof, we can say if we have to do that we don't have to prove anything, and it will type check. And then we have apply function uses proof goal. According to this proof, it's transformed the goal getting a new goal. What apply does it traverses the proof tree, and additional it applies current inference rules. That allows us to update, to incrementally update our proof tree based on the current goal. So if we apply invalid proof to the goal, this will result in an error. Or if the proof is valid, we will get an empty goal. Okay, I cannot show you how it works. So on the right side, I have Pascal interactive environment. On the left side, I have Pascal file that I can modify. So here I make my goal for the example we saw earlier. And now we can incrementally do the proof. At the beginning, we can say to do to actually mean that we have a fault in output. If we now reload and use function apply to our proof. That's our lemma. We get that goal from the earlier. Now we can change this to do to apply implication introduction. We need to state how we are going to call this assumption, and let it be just assumption H. And then we need to put this to do in order for it to say that we don't know the rest of the proof. So when we apply this proof now, it splits it into two parts. First is the list of assumptions, named assumptions, and then our conclusion. We can now change this to do we can now put this actually we can now introduce this conjunction here. And then we need two proofs because now we are splitting the proof tree into two parts. And now we get two sub-goals. One that have conclusion for all x px, and then the other that have conclusion for all x qx. And now we can introduce this for all. To introduce for all, we have to specify a new meta variable. We are going to introduce here a, and then we are going to have some proof to it. So now we have our goal change from this to this, and we have a new meta variable a. We can read this like fix a and then assume age, and then you have the proof that pa equals. We can now eliminate this for all from the assumption age. Now, if we see the function calls elimination, it takes two strings. One is variable, meta variable, and the other is assumption that we are going to apply. And now we here instantiated this meta variable a, and that eliminated cross assumption. We can continue. We can now eliminate this conjunction from the hypothesis A. So we get something like this. We now splitted this into two hypotheses, H1 and H2. And now we can just apply exactly this hypothesis H1 together result. Okay, so now we don't have any more this sub-goal. We finish this this branch, and now we have just this sub-goal. And we can do it the same way. First apply this introduction for all, and then elimination for all, and then conjunction on age. So we get something like this. Now we can just apply exact age to it. And that finishes our proof. We now have nothing left to prove, and we can now generate LaTeX proof from this. To generate LaTeX proof, we need to specify a proof and the goal. And what we get is this nice LaTeX code that we can add to our document. So we did all this. And then we generated LaTeX 3, and we get something like this. So what's the difference from that other proof that is written by hand? Is first we have meta variables printed also. Second is that elimination for the conjunctions actually eliminates conjunction from the one of the assumptions. It doesn't change conclusion. So what we get, we have formal way to write full proofs using natural deduction rule, and we have a way to export it into a LaTeX proof tree format, and this is very minimal software that could be formally verified. What are some of the challenges? For now, we have just this one proof style. The goal is to make many more proof styles and from what I showed at the beginning. There is now it's very tedious to go into interactive environment and then to the file and then so back and forth. So it will be nice to make some plugins for this, possibly for the VS Code or Emacs or Vim or something else. So there are a lot of things that can be done from now on. I also would like to hear from you where this project will go, or if it has any meaning. One thing that we could do is maybe one challenge, maybe to export proofs from the existing proof assistance to the proof assistant Theodore, and then to export the LaTeX proof trees. Those some of the related work. There used to be a couple of softwares for this. For example, this just another proof editor. It's very old, but last time I checked, it did have something, but there is a problem that none of these software actually export LaTeX proof trees. As far as I know, only this software trap actually export Coq proofs in the LaTeX proof tree manner. Jorgen is also have his own software, so I think he will talk later about it. And this paper proof is also is an interesting software that actually visualizes Lean 4, and it makes easier to write than actually writing formal proofs. Okay, that would be it.
Question? Yes, welcome.
So I worked in the 90s with a proof editor called ESCA, proof editor for sequent calculus, which was an appendix to the structural proof theory by Plato and Saranegro. And there is an proof editor works on sequent calculus, but you can then export the natural deduction proof in LaTeX style using the so that's maybe
Yeah.
But then I had I can show you if you can't find it other way. But I was just wondering one thing about this the way this works. So it seems that you build your proof in the code editor and then you reload that module every time you have the step. So did you consider having a loop where you maintain a state where the proof because then you could actually export this as a standalone program. Would not need the user to have a Haskell compiler.
This is probably something.
So that would be needed.
It will be great, and it will be more usable. Now it's very tedious to go back and forth, and also we have these dependencies. But this is very early. This project is maybe less than 3 months old, so and not like full-time work on it.
Another pointer that I could also give, so that you have the complete. So in the predecessor of the Agda, there was actually a visualization as natural deduction in the 90s. So it's no longer supported as far as I know, but it was.
Many of these.
Current Agda doesn't have it.
I searched for this, and there is like maybe online, but I couldn't access it. It's deprecated probably.
I can show you a link where you can get.
Okay.
Because my colleague, my former colleague Thomas Hallgren maintains it.
Okay, nice.
But it's really strange that it is not supported currently. Wait.
With all these pointers systems, I'm maintaining the Theorem Prover Museum, which kind of collects Theorem Prover source codes. So I can invite people, if they find something that's not on there, to actually see that you find the source code, put it there together with a little bit of metadata. It's not that much work. We're in danger of losing our history. It is essentially just an overlay over GitHub repositories, but we shouldn't lose our old source codes. So if anybody has, just if you Google for Theorem Prover Museum, that should be the first hit. And if you know the source code of any theorem prover that's not there, talk to me.
See how you make Stanford people open proof. Put something there.
Yes, it's not always easy to get people to license their or at
Because
least
I think
give out their source code.
that doesn't allow Chicago.
Possibly.
But I think that probably Chicago doesn't allow them, only the grader. The grade grader. The others, they should be able to do it.
Well, I think we have a responsibility as scientists to conserve the history.
Yes. I will send them an email, your suggestion. See how they will. So thank you very much, Andrija. It's a very nice work. I encourage you to continue. So now is the next speaker. Or
We
maybe
have
discussion or
Hello. Okay.
what is the passion? Discussion.
This discussion, sorry, yes.
10 minutes. It's good time.
No,
You can make it in a graphic. Just look at what you can do like that again.
Sorry, what?
Look at what OpenProof people Stanford have done. I think it is very nice rather than going back and forth because we have so the natural deduction there is pitch.
still source code is
Need to
comes from versions. It's
pitch notation is very good because it's
But I have the source code to logical theorists, and there's no computer in the world where this your RAM this thing running. So,
But actually, I refreshed this test guide a few months ago. Put it on GitHub.
okay,
check.
good. And it's mainly mainly GitHub repositories plus a kind of this big YAML file.
And I also so there was this period intermediate this will only exist in personal that would be very and it has a great graphical interface and visual.
Okay. Yeah, we should insert these things because people go
Josh was going back and forth talking generally about funding and how we should talk about like really getting funding from generally. It's like he thinks the meeting is valuable, but it's like, I don't know that I'm funding any of Jim's